Hello and welcome to another Real People Big Astronomy program. My name is Renee Kerrigan. I am a member of the Big Astronomy leadership team. I am the planetarium director and the curator of science at the Peoria Riverfront Museum in Peoria, Illinois. But I'm also a member of this fantastic National Science Foundation funded project, Big Astronomy. Big Astronomy is a project that funded by the National Science Foundation. The goal of the project is to help people understand that there are these fantastic observatories built on the Andes Mountains in Chile, but that the observatories are great science is being done at these observatories, but they are nothing without the fantastic and diverse staff that makes the observatories work. So it takes people all around the world to make big science and big astronomy happen. And so we are excited to get to talk to some of the staff that works at those observatories and learn a little bit about their job and a little bit about their life outside of their job and outside of astronomy. So today we are featuring Peter Moore, who is an electronics engineer for NOIRLab and works on several different telescopes at NOIRLab. Welcome, Peter. Thank you for being here today.
Yeah, thank you very much, Renee. Hello to everyone.
Just a little bit more about Big Astronomy. We have a website called bigastronomy.org in which you can learn more about the project. We have a planetarium show that was filmed in both English and Spanish. And it's being distributed for free or very low cost around the world about these observatories and the people who work at them. We have educational activities that were created by the Astronomical Society of the Pacific. And the whole project, there's educational research that's being done in it by Michigan State University. And you have a chance to contribute to that educational research today, and so we'll talk more about that at the very end of the program. But let's go ahead and get started now with our conversation with Peter Moore. So I'm going to start sharing my screen so that we can see some pictures that we've put together, that Peter put together for us. Can everybody see my screen? Looks good? Okay, great. So Peter Moore is an electronics engineer who specializes in visible and infrared detectors used with astronomical instrumentation. He works at ARA, NOIRLab, which is a consortium of different observatories, and has helped create the detector system for the dark energy camera. And I have a great memory of getting a tour of the optics lab at Gemini South outside of La Serena at the headquarters there, and getting to talk with Peter back in 2015 about the dark energy camera and the detectors that are used. So I'm looking forward to learn more about your job today, Peter. So thank you for being here.
Oh, thank you, Renee. Yes, it's a pleasure to be with you. Would you like a job?
I do have a job, but it'd be probably hard to go to Chile, but it's a pretty fantastic place. I'd like to visit more often than I have, is what I think I'd like to do.
Yeah, it's a beautiful country.
So to start us off, can you just tell us a little bit about yourself?
Well, as it says on the slide, I'm an electronics engineer, and I didn't start out with the idea of working in astronomy, but I've ended up here. And the idea of being an electronics engineer is quite generic. With the specialization that I've ended up acquiring through knowledge of detectors, I now have become so specialized that they call me a detector engineer, which doesn't mean to say I don't deal in electronics, but it branches into the area of physics and astronomy and sensors. Yes. So for the last I can't remember how many years I've been working on the detector systems for telescopes. Now, a detector for a telescope is the last thing that a photon sees before it becomes converted into an electron. The photons which we capture is the only signal that we have to analyze the universe around us. And so these photons are generated in some maelstrom of atomic activity, or by other physical phenomena. And they travel for various lengths of time and long amounts of time until they pass and are captured into the mirror of the telescope, where they become an image inside an optical instrument, which is designed to do some manipulation of the signal, the optical signal, whether it be something like spectroscopy, where we're looking for the wavelength, the energies that we are receiving, or whether it be imaging, for instance, where we're looking at the displacement or the shapes. There's a variety of optical instrumentation that's used. And finally, those photons, which make up that image, impinge on a piece of silicon, which is specially made in a way to receive the photons and convert them into electrons. And the detectors in general are no different in technology than the ones we have in cell phones and in the computers for this, for instance, video conference. But they are much larger and much more specialized, and we have to separate each photon, which has been traveling sometimes for billions of years, from all of the other noise that's being created by the electronics, by the sky, etc. So that's my specialty.
And it sounds like a challenging job, because I'm sure there is, with these big machines, so much noise that they make, that the optics would have to be smart enough to separate out.
Yes, and the key, the the principal paradigm that we use to refine the signal coming from space is to reduce the noise sources and the influences, optical aberrations, etc., before that the photon suffers before it becomes converted into an electrical signal. And that electrical signal is stored like any other image on a computer, so we can analyze it and process it to extract information, scientific information from it.
Well, Peter, can you tell us a little bit about your path, how you got to where you are today? I know you have some words there, but maybe you can just share with us, in your own words spoken, like how you ended up working in this field that you didn't necessarily think you would start off in.
No, I didn't have any idea, apart from, as a young lad, looking up at the sky and wondering what it was. Um, Astronomy didn't actually cross my path until 26, 28 years ago or so. My career towards this was, once I got off the idea of being young forever and living on the beach, um, really went through a phase which was kind of confusing when I was young. As I stayed there, I knew what I needed to do, but I had no idea what I was going to do with it. And then one day, while I was working, I was offered a position with a seismic exploration crew, Western Geophysical. And that company did oil exploration for clients and put me on a ship, which was something I wanted to do, as an electronics engineer, which was something I wanted to do, and liberated me from girlfriend and all of the renting the apartment and so forth that I was really into. And that's where I suddenly found the opportunities to self-study and find out more about what I was trying to do, because I was quite green, very green. And that led me into geophysics. And from geophysics, I don't know if you can say graduated, but I moved from offshore geophysics, which was involved in maritime operations, um, to airborne geophysics. In the meantime, it had also enabled me to start traveling, which was an eye-opener because I had had a dream to go and look at the world. But now I found I could actually do that and be paid for it. And so from airborne geophysics, I ended up in Chile in 1986. Yeah. And mucked around a little bit with telephone companies and so forth. And then I happened to be passing the observatory of ESO up in the north, and decided that was pretty good looking to be able to work on top of a mountain in isolation from all the noise that was down on the cities. And I was fortunate enough to be able to apply for a job there and get it. And then, of course, specialized in the detector side. But all of my life, professionally, I've been involved in acquiring signals from physics. That was the core of the whole thing, whether it was geophysics or whether it's astrophysics, or just simply, for sometimes in telephonia, in the telephone company, just looking after sound and audio, but it's all been physics, sensors.
That's such an interesting way to put it because your careers have been varied, but there is a connecting thread
Yes.
for all of them. And I love the idea that your scientific career has helped you travel the world. I think probably a lot of young people that might um, resonate with them. At least I know it's appealing to me. I've lived my whole life in one spot, so I love hearing about people who've had a chance to travel all over with their careers. It's very interesting.
Yes, the travel is marvelous because it suddenly opens up your horizons. You suddenly find people living the exact sort of same life as you are, but under different cultures and different circumstances sometimes, and it opens your mind amazingly.
Yeah, hopefully we can all get back to being able to do that again. Maybe this
Yeah.
year. Fingers crossed. Knock on wood. So what would you say one of the biggest challenges has been in your career, and how were you able to deal with that?
Well, as I state, on the professional level, technology in general is an impressive uh, rate of change. And if you're just following one side of it, then okay, then you might be able to keep up current with what's going on. But there's most of technology actually involves a lot of other things as well. Be it, for instance, in detectors, a lot of it depends on materials and the way that we create or modify materials to do what they want we want them to do. So there's sidelines, and one of the largest challenges that we have as engineers is to maintain um, ourselves on top of what is going on around us and what are the possibilities in the future. And then at a personal level, yeah, it's hard to actually um, you can't work all the time. So you have to you have to dedicate yourself to something else. And in my case, that was family. So the balance of staying professionally agile and at the same time providing a decent living for my family was also trying sometimes.
I think that's probably something a lot of people, no matter what their profession is, can probably sympathize with. That we're all trying to find that balance.
Mm.
Oops. Let's see. So, what is your favorite thing about your job, and why? You have a lot of good pictures here, but to a non-detector engineer, I have no way of interpreting them. So I'm curious.
Okay, I didn't mean to confuse people. I hope people can follow this. The favorite thing about the work I do is the actual design or the creation. because as an engineer, you're charged with taking some concept and producing something physical or substantial result, which is either visible, weighable, or in some way present. So the creation of the job is, I really find special. So if you start on the left-hand side of the slide, there's a question mark, and that sort of says, well, what if we do this, or can we do that, or we need to do that? And you go through a stage of investigation, looking at technologies, for instance, or methodologies. In engineering, there's quite a few which are predefined, but you can always break the bucket and be innovative as well. And so that leads you to a design, which then, as you move to the right-hand side of the page, becomes a physical entity. And in this case, the schematic in the middle between the question mark and the right-hand image is an actual circuit diagram of the small part of the thing on the right, which is we call a torrent controller. And this is a piece of equipment we use to control detectors. And the organization I work for, we embarked on a development scheme to build our own controllers so as to have control of them and normalize them across all of the telescopes that we have operational. So the realization of from going from an idea through the design into the physicality of the device and then putting it to work. So the next item on the lower left-hand side of the screen is actually a picture of a detector. And this then mates to what you built and gives you results, which you can see on the center and the right-hand side. The graphs are really nothing to do with the detector, but they are identified with what we deal with in detectors. So the middle graph, for instance, is the radioactivity or the emission of glass, different types of glass, which we see on the detector. So we want to minimize the emission from the glass window, which is in front of the detector. And we do it by measuring the radioactivity of glass. And then on the right-hand side, you can see the same piece of glass and the transmission of light through that glass in terms of wavelength. So that's the favorite thing about my job, is being able to take concept and generating real live functional pieces of equipment and then seeing how they perform.
I find that so interesting, and I'm curious. For your job, you create these concepts. Would you actually build that first initial build, to test it?
Yep.
And how about the drawings? Is that part of your job? Do you create those drawings as well?
Yes. Yeah. For instance, the drawing that you see, I created that as part of this development opportunity. And then I passed that drawing to a draftsman who was in charge of laying it out on a printed circuit board. And his job was to collect the information about the components, place them in while we work together so that we get minimum interference and maximum efficiency on the board. And so this extends to different areas. So once we have that, the design of the printed circuit board, we usually push that outside to be manufactured. And then we need to build the actual chassis, which is the metalwork you can see on the other side. We build that in-house, or in this case, we contracted out after we designed it. So there's an immense amount of detail involved in that design by a team. It wasn't just me, there was a team of 5 of us doing that.
A lot of work, but probably very rewarding when you see it completed and across the board, as you said, then it's implemented probably in many different telescopes. I imagine that's very rewarding.
Yes, yeah. The first time you turn it on, you need a fire extinguisher next to you. If you don't use the fire extinguisher, you're on the right path.
Good life advice, I think. So, as a sort of opposite side of the coin, your favorite part of your job you've described, having a concept, coming up with solutions, and seeing it through all the way to the completion and having results. So, what about the least favorite part of your job and why?
Oh, do I need to say more operating systems and the computer infrastructures? Because at NOIRLab, we have literally hundreds of computers. And we have one group which administers those computers and tries to do their best to maintain them, keep them all running order. And part of that mandate is to try and normalize all the operating systems and the way that we interact with the computers. Well, we use a lot of the computers as acquisition systems. That is, they acquire the data from the detector controllers. And so we have very special requirements for these computers in the way that their speed, their interfacing type, the hardware that they have to talk to intimately, etc. And every time you try and change an operating system, it brings on chaos. So yeah, that's the least part of my job, is to trying to work out how you can take a 10 or a 12-year-old piece of equipment and then update the acquisition computer, because the old computer style has gone is obsolete. You can't find them anymore, and get them to work with a new operating system. Sorry,
No,
Renee, you're mute.
no automatic upgrades to the new Windows system for you. That
Oh,
sounds.
I'm still fighting that.
So, how about your favorite astronomical objects? What are some of your favorite astronomical objects?
Okay, well, because we work in astronomy, you can't help but be awed by the universe around us. Um, I don't know if anyone who's listening is familiar with Douglas Adams and Hitchhiker's Guide to the Galaxy, but one of his quotes is very uh, is very sharp. He says something like, here we stand on a ball of dust rotating at thousands of kilometers per hour and orbiting a huge hot mass of of gas, which is boiling at millions of degrees Celsius, and we consider this normal. And that is how the universe is. So the favorite astronomical objects that I've selected here are sort of a melange uh, of different aspects of that. The first one is the jewel box, which is, I think it's NGC 4755. That's the catalog number for it. And essentially, when you look at it with the naked eye or with a moderate pair of binoculars, you can see up to 6 stars. But there's actually over 130 stars in that cluster. You only see the 6 because they are bright enough. They have magnitudes which you can capture with the small pupil size of your eyes. But it's a beautiful twinkling jewel in the sky. And you can use it to actually gauge what the sky conditions are like, because depending on how many stars you can actually see, then you can gauge what the atmosphere is doing, how clear it is, what the light pollution is, etc. So if you can't see any of the jewel box, then you're really in bad shape. Your night sky is very, very dull. That's the jewel box is just west of Orion's belt, so you can locate it over there. The center picture is actually an image of the jewel box, so you can see what I mean by being this bright piece of jewelry hanging in the sky. And on the right-hand side, the small image is a galaxy. And all galaxies excite me because there's such a massive amount of energy and material and dynamics going on in these objects, in the whole universe. I mean, we're made of billions of galaxies and absolutely astronomical, if you excuse the pun, number of suns and stars. So the other things the things that excite me about galaxies is the massiveness of it and the raw power in it. There, we talk about, electricity bills which run to maybe 20 or 50 kilowatt hours per month of your house, and that's over in sort of a nanosecond in these systems. It's just incredible the amount of energy which is contained and being used in those structures. And the last one is, I don't know if anyone recognizes it. Does anyone recognize that, the blue and green orb you see there?
I don't see any
No?
comments coming in, folks. Oh, so
Well,
Vivian says it's Earth.
yes, it is. It's one of the most precious astronomical objects that we have, and so that's why it's there. It's a jewel also in its own sense, in that it's the only known astronomical body that we know of where life, as we can describe it, exists. So please look after it.
I love that. I like to end in my planetarium. I like to end my tour of the solar system with Earth because I like to remind people it's the most unique, the most special planet in the solar system. The only
So
one with
far,
liquid water on its surface, and the only
yeah,
one that we know of with life on it.
very good. I'm going to come to one of your planetarium sessions.
You're welcome anytime.
Thank you.
So I love your selection of pictures for what you've put up with for a typical day at work, because I'm getting the sense that there is no such thing as a typical day at work for you. But can you tell us a little bit about what your day at work might be like?
I think it's probably, apart from the engineering aspect with regards to the astronomy departments, it's pretty much the same. It's report writing, it's email, it's coffee, it's revising things. But I've thrown a few other things in there, which are maybe worth quoting or worth telling you about. Um, the saying there, research is what I'm doing when I don't know what I'm doing, is very, very true. And that's sort of exciting, because when you know you don't know how to do something, then you go look to find how to do it. Now, there's a very huge pressure nowadays to go on YouTube or Google and Google it and see how someone else has done it. But that's not often the best way to do it. Certainly do that, but then the idea is that if you're doing research, you need to think sideways and start looking for innovative ways to solve whatever it is that you're trying to find out. And that's a part of the work that we need to do as engineers here. On the right-hand side, that's a circuit diagram, one of my favorites from the cartoonist. Immediately adjacent to that, overlapping that is a picture of the Blanco telescope, where we spend a lot of our time. That's where the dark energy camera is mounted, and we need to do maintenance and quality control and maintain the telescope during the day, so that during the night that it operates flawlessly. And so that occupies my days sometimes as well. The one on the bottom, which is revising instrument telemetry, we've been able to instrument a lot of our systems such that we don't need to leave the office to understand how they're performing. And that helps us a lot, because not only does it provide us with an instantaneous view of the parameters which are going, or the parameters which are being um, used by the systems, but it also gives us a history of what has happened. And that allows us to maintain a very, very good quality control system, so the images and the data that the scientists take away from the observatory can be, we can have a high degree of confidence that they are reliable data, and they can base their analysis on it. And the one in the middle, buried underneath everything else, is actually with the thumbs up. That's because as an engineer, you end up solving a lot of other people's problems. So people will come to you with their problem, and then you're expected to solve their problem. So that's the other part of the life of an engineer.
You mentioned the dark energy camera and that a lot of
Hmm.
your time is spent maintaining it, so it works really well. Can you just, for some of our viewers who might not be familiar with that instrument, I know that that's something that you worked on extensively. Can you tell us a little bit about the dark energy camera and what it's doing?
Yeah, the dark energy camera was born out of an initiative when we realized when the astronomical community realized that the acceleration of the universe was not slowing down, rather it was increasing. And this was found out through the background microwave energy experiments which were done initially. And there was a lot of guessing. And then finally, they come up with the idea that there is an acceleration to the velocity of expansion of the universe. That led to a few people got onto their calculator and did the sums and found out that there was not enough mass and energy in the universe to actually account for the acceleration that we were seeing, which was disconcerting because we thought we knew everything. Um, and then there was this coin termed at one conference called dark energy. And that lit off a tremendous effort, which still is going on today, to find out the origins and the influences of dark energy. In other words, that which we can't smell, touch, see, measure, or even interact with, which is powering this acceleration, this apparent acceleration of the universe. It may be that we're dead wrong, but that's the consensus of scientific thought at the moment. So the dark energy camera was born to investigate this phenomena. Essentially, what we're doing is that the influences of dark energy are such that you can measure the effect it has on the universe by some discrepancies in the positions and the if you like, the positions of astronomical objects. And so to gain the precision of the information we needed 6 years of data from the dark energy camera. And that program of survey was concluded, I think it was last year, maybe the year before. So in other words, we've been running the dark energy camera for 6 years continuously, looking at the same pieces of sky and stacking up all the images to reduce errors in a way that allowed us to discriminate between natural phenomena we knew about in the universe that is governed by the physical laws we know, and that which is strange because it's governed by the influence of dark energy. Though that data, that information now has resulted in some substantial findings and affirmations of some of the theories related to dark energy. Nowadays, the dark energy camera is used by anyone who wants to use it and can apply for it. There's a system of qualifying the experiment you want to carry out on using that camera. But the dark energy camera is being used for wide field surveys and for specific wide field objects that need to be taken or to be studied. So it's an exciting instrument. Um, the next instrument to come online to be dedicated to this is what we call the Vera telescope, which was originally the LSST, the Large Synoptic Survey Telescope. It was renamed, and that will come online and do a larger piece of sky with the same sort of investigation. That's optical imaging, to further refine the data and to try and make some sense out of dark energy, which we can't touch, smell, see, hear, or at the moment find.
It's very exciting, and the technology for the dark energy camera, and then the new Vera Rubin telescope. It's really amazing. Just when I was lucky enough to see the Blanco telescope with the dark energy camera on it, I remember they were observing, the secondary mirrors replaced by this camera, right, with these
Yes.
enormously high resolution. I'm sure you know the resolution, enormously high resolution camera.
It has a very wide field of view, which is what you're talking about. Resolution is resolution on sky is we measure in arc seconds, and it that's limited by the conditions of the atmosphere we can see through. But yes, you're right. It has very high resolution and enormous field of view.
And they're observing the night sky, and just a tiny little section of the image they were observing in, and then you zoom in and you can see this amazing,
Oh,
beautiful
yeah.
object. So it's exciting that the primary survey has been completed from the dark energy cameras, and all that data. I'm sure is going to take a long time to sift through and mine, and then with the Vera Rubin telescope coming online soon, I will have even more hopeful data to help us answer that question about dark energy,
Yes.
or at least make
Yes.
more have more questions.
Oh, yeah. There's bound to be more questions.
Okay, so you've told us a little bit about your day at work. We'd like to try to help our viewers understand that the people who work in STEM careers, they're whole people. They have lives outside of their jobs. So that's why we ask, what about a little bit about what your day at home might be like?
Um, it has changed over the years because my wife and I have three children, and so I've tried to symbolize that on the left-hand side. This is one of our sons. This is Leo. Um, we try to be we've gone from living together, in other words, a family of five, to now being just the two of us. That's part of getting old and having your children find their part in the world. But family life is a large part of it. We try and maintain contact and help each other out and so forth. Um, when I'm not working, then I like to try and read books. Specifically, I oscillate between Christianity and science fiction, and sometimes a little bit of murder and whodunit. Um, the image on the right is occupying a lot of our time at the moment because that's a house that we're trying to build. We've been occupied with that for some years, and it's never going to be finished, but hopefully one day we'll move in. Um, and it's just lovely to sort of take the time sometimes to go and walk along the beach when you can. Of course, the pandemic has caused a rupture of that idea, or go to a restaurant or have a barbecue, invite some friends, that sort of activity.
All right. Well, how about
Ah,
your favorite subject in school? What did you like to study when you were in your schooling?
yeah, I used to love technical drawing. I like the precision of it. And I used to like woodwork a lot too. I think mainly because the teacher was so um, accommodating, if you like. He would show you things that if you showed interest, he showed interest back, and that was really good. And I'm surprised. I've written here a sort of a question because I'm surprised that the curriculum of most schools that at least I know don't include such themes nowadays. They concentrate on theoretical and abstract concepts, but nothing to do with the practicality of what you do in life. And one of the things I found out is that if you want to be good at something, you've got to start at the bottom. And the best place to start at the bottom is when you're young, because you absorb things a lot easier than if you're an old folk like me. So it's a shame that I find it's a shame that such curriculums or subjects are not included in today's curriculums on a widespread basis. My wife Mirta tells me that she used to take home cooking, But now you can't have home cooking classes without being offensive in some way, and or it's a possibility. And that's not the point. The point is that once you found out how to cook an egg, then you can go on from there. Um the first one's bound to be a disaster. The second one, maybe. By the time you've experienced this exposure to these practical things in your life, it needs to be at an early age, not later on when you're on the streets and need to find yourself a meal.
I think that in some cases those sort of technical classes are starting to make a comeback in schools. I agree with you that there's been a um, sort of purging of them from our school system and our curriculum. But I think they're starting to make a comeback. At least I hope so, because you loved in school technical drawing and woodworking, and look how that is now a part of your career. You
Yeah,
use those skills still, and I'm sure that helped influence you in the careers you chose. So how about?
yeah.
Oh, sorry.
Mo I'd just like to say another thing there, and that is that you know the interest in these subjects. I don't think you can study a subject and be successful with it unless you have an interest. And the interest for me, I need to make a big shout out to my father. He showered on me all sorts of things, which some I didn't like doing, digging ditches, but it was all part of an education, and I didn't realize at that time. But the experience gained when you're young in that sort of area where you can learn things and have an opinion about them, and then people maybe make them work for you, is starts really also within the family culture.
And I think that's so true. So all the parents watching, keep encouraging your children's
Mm,
curiosity.
yeah.
So how
Ah,
about your least favorite subject in school?
yeah, I really didn't like chemistry. Um, I had a teacher who I'll even name because I don't think he's alive anymore, Mr. Rapp. And Mr. Rapp, if he couldn't teach me chemistry, he'd cane me.
Oh no.
And that didn't go down too well. So I don't think I ever got any good marks in chemistry, but I did love physics because, as I've stated there, it gave me an idea of how to apply understanding to things I saw every day,
Yeah.
whether it be a car rolling on the street or a basketball floating across a court. There was understanding in physics, and that's why I love physics.
And you also touched on two other things that I think are so important, that in your favorite subjects, you had good teachers who took an interest in your learning, and in one of your least favorite subjects, the opposite was the case.
I hope
Okay.
Mr. Rapp's watching.
You mentioned a little bit about this already. So, but about what you like to do for fun. You like to read and time with your family, and building your home.
Yes, and the fun part of it, the extraordinary part of it from everyday life, is really a mixture of music. Love music, any type of music I can respond to. Um, I come from that age where Pink Floyd, Moody Blues, Led Zeppelin were kings, and that's still there as a core. But I appreciate music from every part. And then travel. We've been very blessed to be able to go with our family to different countries and explore, as I said before, different cultures, find out things and see wild animals in their natural habitat, swim in places that you wouldn't otherwise experience. So that's been a very, very nice part of our life. And if there's nothing else to do, then the beach, where you can just watch the surf, lay down in the sun, listen to what's going on around you. That's great too.
Well, our last question is one that I think you added, Peter, which
I
is
don't think you should show it. Oh, too late.
words of wisdom that you might like to share with our viewers.
Yeah, notice the question mark. Since we're dealing here with all of you who are hopefully still listening, um, the idea of looking at scientific careers or engineering careers, that is those which require you to actually think, then these are words of wisdom I think I should give you, and that is you don't get yourself in a space where you need to do something because you feel pressure, well, not only pressured by or pressured by circumstance. Yeah, sure, you're going to go hungry in your life, but don't work for a guy who forces you to wear a tie if you don't like wearing ties, because you're not going to get out. The best thing is just to suffer hunger and use your inventiveness and your abilities to find a way into areas that you do want to work in. Because man, you're going to be working for 40 odd years, and you really don't want to get into something which is going to be distasteful for you every day. So the second part is, yeah, to try and look for the opportunities that present themselves and go for it. Don't hold back. Just throw your whole towel in and be exuberant and right over the top to get in and take advantage of those opportunities when they exist. And if they don't exist, try and make your own by tunneling under um, areas where you're supposed to be prohibited, not allowed to tunnel under. For instance, corporate barriers and this whole process of uh, applying for jobs or careers through a front line, which is human resources, which all they're doing is putting you through a machine. Try and find the guys and the people who are the guys and the girls and the people who are in charge of this and go directly to them. Make your own opportunities and never fool yourself. Um, be yourself, and that means not turning yourself into somebody who follows just other people because that seems the easiest thing to do. You know, life is never easy, but while it's going to be hard, you might as well make it worth your while and do your stuff that you want to do. That's it. Have
And
fun.
don't forget the last bit, have fun.
Yeah, yeah. Yeah, there's only one life given to us as we know it. As a Christian, I believe in an afterlife, but that hasn't been proven. So the scientist in me says,
We have some questions for you from our
"Oh,
viewers.
good."
So, if anybody has questions after watching and hearing from Peter, please just leave them in the chat. If you're on Zoom, if you're on Facebook, just leave them in the comments and we'll try to answer them. So, one of the questions from Stephen on Facebook is, what is the typical size of a detector? What is involved mechanically in building, moving, and installing? What are things that go wrong along the way? So that's a lot of questions I'll put into one.
Okay, I'll try and be brief. The detectors are getting ever larger. Nowadays, we have scientific quality detectors up to 9,000 by 9,000 pixels. Uh, that's uh, that's a lot of pixels. Um, the problem with larger devices is getting the information off them, because depending on their architecture, whether or not they're CCDs, that's charge coupled devices, or CMOS, depends on how that is done. But even so, uh, there's a balance that we try to achieve between the quality of the detector, which determines the capability of the instrument, and the size, which can make a difference in terms of the scope of the science you're doing as well. What goes wrong, or how do we do the mechanics? The detectors are very precise. They are flat to microns. We have to preserve them as very clean and very a precisely mounted object or device inside usually a liquid nitrogen dewar or some sort of vacuum dewar that allows us to create a vacuum around it and isolate it, because we cool them down to minus 200 degrees, some of them on the infrared, minus 100 130, 160 degrees Celsius for visible detectors. What goes wrong? Well, Murphy is there. He is alive and active. So some of the things that go wrong is usually to do with mundane things, for instance, vacuum systems, seals, maintaining a vacuum, electronic systems, it's getting rid of noise, making sure you're getting the optimum performance from the detector. For instance, the detectors have a balance, everything's a compromise. So there's a balance between how many photons you can collect and, for instance, maybe the dark current, which is the signal that the detectors themselves, even though they're very cold, produce. So everything's a compromise. You try and work this in, and the things that go wrong, you either fix it or start again. Hope that helps too.
Okay, we have another question. Some kudos on your words of wisdom, and in particular, the knowing yourself part was appreciated. So let me see. There's another question. Can you tell us a little bit about major discovery that has been made? And I'm sure there's more than one, but any major discoveries that may have been made with some of the instruments that you worked on, some of the detectors you helped create.
Yeah, I'll tell you two. The first one was a novel detector that we were trying out on a telescope, on the William Herschel telescope. And this was what we called an STJ, a tunneling junction, superconducting tunneling junction. It was a very small array. It was only 6 by 6 pixels, but it allowed you to visualize the energy, the time of arrival, and the position of each photon which arrived. And so this was a test because they wanted to try and, it was by the Technology Center for ESA. And they wanted to try and propose that they mounted these and sent them into space on the Hubble refit. So we were testing out the detectors to try and prove them, characterize them on sky. And we actually watched with this detector a binary system. That is where we have two suns. One that is they're orbiting each other. And the two suns were slightly different materials. I can't remember what their classification was at this time, but you could tell by the light coming from them which sun was which. And we watched in real time as these two suns crossed in front of each other. And that still gives me shivers. That's thousands of millions of kilometers away. We saw it happen. Amazing. The other one was actually also at the William Herschel. I don't know why I've picked these two, but okay. We had a very stable spectrograph. This is a machine, an optical machine, which separates the energies of the photons which come in and allow us to classify sometimes how the photon was made, what process or where it's been. And they used this to actually detect the first exoplanet. At that time, exoplanets had not been seen. And the way they did it was that they used the sun as the main source, which is logical. And then they used the reflection off of the orbiting planet's surface, the albedo, to detect as that moved around because it altered the spectrum. So we were able to detect the rotation of this planet around this sun, simply looking at the frequency of the change in the spectra of the star.
watching those results come in must have really felt amazing. Just seeing those live results from something that you had helped create.
Yeah, that was amazing. Yeah.
We have a comment from Chris Packham. He says, "Please say hi from Texas. Peter and I worked together on an infrared array for an instrument called Ingrid about 20 years ago."
That's right. Hi, Chris. What are you doing here? You go back to school?
And I think maybe one last question from a viewer who's a student. Can you mention some technical skills you feel that current engineering students like me must focus on or develop to get into the career of electronics engineering associated with astronomy research? Thanks for the wonderful talk.
Oh, you're welcome. Um, well, the first skill you need is intelligence, and that's not something you're born with. That's something you grow. Um, the more that you use your brain, the better it will become at discerning opportunities, um, solutions. I'm talking here as an engineer, um, and so you need a brain, and you need to have it agile. So once you have a brain, then you need to feed it, and you feed it with, in the case of wanting to become involved in astronomy as an engineer, then there's many fields for electronic engineering in astronomy, from things like servo mechanisms. You might see this telescope behind me. That's the Blanco telescope. That weighs approximately, I think, about 320 tons, and yet you can it's driven by a couple of motors which are less than half a horsepower. You can actually move the telescope with your finger if you've got a tough finger. It's so well balanced, so precise. So there's a lot of engineering, a lot of electronics in astronomy that you can apply yourself to. And the areas most used in this area are basically, I think, things like motion control, um, detectors and instrument control. By that I mean detectors obviously are what I've just talked about. Instrument control is getting things like samples of the wave fronts off of the mirrors so that you can adjust the mirrors to get a perfect surface for the collection of the photons. Um, this all has to do with working with computers, so you do need computers and skills, programming skills, as apart from being electronics. Um, and I think the best way to get it, as an example, um, one of our sons, was very interested in aviation, and when I suggested that he go down to the local airport and wash airplanes to get into it, he sort of looked at me as strange and said, "But I don't want to wash them. I just want to fly them." And that's not the right attitude. If you want to get into astronomy, in particular as an electronics engineer or to do with electronics, then start making friends with all people who are into astronomy and think like you, and get yourself into that culture, and you'll find a way. You'll get there.
Well, thank you so much, Peter. We really appreciate your time today. There's a lot of really positive comments of people who really found your conversation interesting and enjoyed your passion and learning a little bit about sort of a behind the scenes look at a job at the observatories. We do need to close. We're coming in on the hour. So I'd like to thank our viewers. And
Yes.
Dr. Shanna Schmoll is going to pop on here and tell us a little bit about the research that's being done on this project.
Hi, everyone. Thanks for having me on. I am from the research project, or the research end of this NSF-funded project. So we are studying the planetarium show and the live events and all the different resources that go along with it. And so if you'd like to help us out, we would really appreciate it. We have put into the chat on Zoom and onto the comments on Facebook a link to a survey that you can fill out. And if you fill that out, you'll have be entered to win a be entered to win a $10 Amazon gift card. So it would really help us out. And there's also an opportunity on there to say that you would be interested in helping us further with interviews, in which case you would be eligible for a $40 Amazon gift card. So thank you so much. And please do go fill out those surveys. We'd appreciate it.
So the links are both on Facebook and in the Zoom chat. And to wrap up, I'll just mention that we have events coming up. So if you enjoyed this today, I hope you'll come back for further events. We'll be speaking with STEM professionals all through the rest of this year in this Real People Big Astronomy series. And we'll also be doing educational activity demonstrations. So the next one of those is on March 10th. Vivian White will be talking about legends in the sky, constellations from around the world. And we also have weekly live streams of the Big Astronomy Planetarium show in 360. So you can watch it on a device, on your phone, or on your computer. And you can find out more information about that on our Facebook page, Big Astronomy on Facebook. So thank you, Peter. Really enjoyed the talk today. Thank you, everyone, for tuning in, and we'll see you next time.
I bet Chris is going for the contest.
I hope so.